Hello everyone, myself Bhavna Rani. This is my teammate Bindu, Divashri, Manasa and Sinchana Poojar. Topic is evaluate and design the solutions for decision making in the self-driving car under the uncertainties using bias reasoning. Biasing decisions making in autonomous vehicles, evaluating the solutions for uncertainty and risk mitigations for graduate students and in the instructors in the autonomous systems and robotics forcing and the probabilistic method for the robust decisions making. Introduction to uncertainties. First one, biasing reasoning, understanding the core principles of using prior knowledge to update brief bias and new sensor challenges, evaluating the impact of noise and incomplete sensors data on the purpose systems. Third one, risk analysis, analyzing the safety implications and incorrect probabilistic prediction in the dynamic sensors. Mitigations and frameworks, assessing the existings and developing the new framework for enhanced reliabilities. Next will be continued Bindu.
Thank you, Bhavna. Now coming to next, explaining bias and reasoning in autonomous vehicles. Concept overview. Bias and reasoning provide a mathematical framework for updating beliefs or probabilities as new data, sensor inputs becomes unavailable. In self-driving cars, uncertainty arises from a changing environment, sensor noise, or incomplete data. Using Bayesian method, the vehicle can continuously update its understanding of the environment to make safer and more reliable decision. Core principle, Bayes theorem. The formula is P of H divided by E is equal to P of E divided by H into P of H divided by P of E. The P of H divided by E stands for posterior updating probability after observing evidence, new sensor data. PH refers to prior initial belief before seeing the new evidences. P of E divided by H means likelihood probability of seeing the evidence if the hypothesis is true. P of E is evidence overall probability of observing the evidence. In simple terms, the cause starts with an initial assumption prior about its environment, collect the sensor data's evidence, and update its understanding the posterior to make better decision in a real time. Next, coming to next slide, application of Bayesian methods. Bias reasoning is used in three major areas. First one is state estimation. Second one is object classification. Third one is intention prediction. First one is state estimation. Determines the vehicle current position, speed, and orientation. Technical likes filters and practical filters applies Bayesian updates to filter our sensor noises and maintain accurate tracking of the car state. Second one is object classification. Help identifying what object vehicles such as pedestrian, cyclist, and other vehicles. Bayesian model assigns probability to each possible object types, enabling the car to make safe decisions like slow down or changing lanes. Third one is intention predictions. Estimates the future action of nearby object or road users. For example, it predicts whether a pedestrian might crosses the street or if the other car might change lanes. This prediction is based on the past behavior priors and the current absorption evidence. The bias reasoning allowing the autonomous vehicles to handling the uncertainty in intelligence combines the prior knowledge with real-time data, make probabilistic data-driven decision for navigation, prediction, and safety. Next, we'll continue by Sinchana.
Coming to the evaluating challenges from sensor uncertainty, We have sensor data is the foundation of autonomous perceptions, but inheriting the noises and limitations introduce significant uncertainty that Bayesian models must handle robustly. So, first one we have noisy measurement, occlusions and missing data, cross-sensor discrepancy, environmental interferences. Noisy measurements. LiDAR and radar measurements often contain random errors, which are Gaussian noises, which directly impact the precision of object localization and tracking. Occlusions and missing data. Buildings, large vehicles, or adverse weather can cause partial or total occlusions of objects, leading to missing data and requiring reliance on less certain priors. Cross-sensor discrepancy. Challenges arise in fusing data from heterogeneous sensors, which are camera versus LiDAR, when there's estimated probabilities or measurement timings conflicts. So, coming to the environmental interferences, severe weather, heavy rain, fog, or dynamic lighting conditions can significantly lower the signal to noise ratio, inflating the predicted uncertainty. So the vehicle's certainty about its environment is only as reliable as combined on processed data from its sensors. Coming to the analyzing safety risk from probability errors, incorrect probability estimations like either over or underestimating risk are the critical pathway to safety failures in autonomous decisions making. Underestimation of risk, overestimation of uncertainty, and propagation of errors. Assigning a low probability to a dangerous event, example, a pedestrian darting out, this can lead to aggressive, unsafe maneuvers or inadequate braking distances. Overestimation of uncertainty, assigning overly high uncertainty to common events, example, misclassifying a parked car as a moving obstacle. This result in excessive caution, sudden braking, or unnecessary disengagements, potentially causing rear-end collisions. Propagations of errors. An error is a low-level perception task. Example, inaccurate object velocity estimation cascades through the Bayesian network, leading to a catastrophic errors in high-level path planning. Evaluating current mitigation strategies. Several strategies are employed to enhance the robustness of probabilistic decision making in real world driving. However, each has limitations. First one, we have sensor redundancy and fusions, safety constraints and formal methods, domain randomization in training. Sensor redundancy and fusions using multiple sensor types, LiDAR, radar, camera to provide the diverse measurements. Here, effectiveness we have highly effective against single point sensor failures, but struggles with the correlated errors. Example, heavy fog affecting all the optical sensors. Safety constants and formal methods. Implementing hard-coded safety constant, example a minimum stopping distance that override the probabilistic outputs when this exceeds the thresholds. Effectiveness we have guarantees basic safety but can lead to overtly conservative driving and reduce efficiency. Domain randomization in training. Training models with synthetic data that includes varied noise levels and adverse conditions. Here we have effectivenesses such as improves model generalization but may fail on long tail cordon cases not covered by the synthetic dataset. So further will be continued by Divishri.
Sinchana. Now coming to the framework for reliability, this section which talks about the correct decisions even when the environment is uncertain. So this means the need of the remains for an ununified framework that integrates the possibility of the confidence with the measurable performance and the criteria to certify the reliability in an uncertain environment. Now going to the next slides, that is a developing a reliability framework for developing a reliability framework and a matrices. So this framework has a three main pillars, that is a confidence scoring, a scenario coverage validations, and a pillar 3, that is a decision auditing loop. So the purpose of the framework is the under which to improve and decision reliability, to measure the improvement decision reliability. Now coming to the pillar 1, that is confidence scoring. This implementing on the episodic uncertainty model ignorance along the alloretic uncertainty, that is a data noise, and the matrices includes average confidence entropy on the core object probabilities. Now coming to the pillar 2, that is a scenario coverage validation, uses a scenario density index to quantify the system's exposed and the validated performance across a different uncertainty states, that is an example of the levels of occlusion and the sensor degradations. Now coming to the pillar 3, that is a establishing of the continuous loop where the decisions are under low confidence conditions are logged with a simulated human review to update a prior and refines the model likelihoods. Now the key metric of this is to the mean time between the low confidence intervention, tracking how often the system relies on a hard safety overreads due to the low probabilistic confidence. Now coming to the next slide, the conclusion, that is towards the certified anatomy. So mastering the uncertainty through a robust Bayesian reasoning and a rigorous metric based framework is an essential for deploying a reliable in self-driving systems. So our evaluation that highlights the transitions from simplifying the imaging uncertainty to actively quantifying and mitigating associated risk. So the key takeaways from this self-driving car is the Bayesian methods are the theoretically is backbone for handling of the inherent sensor noise and an environmental unpredictability. The safety risks are primarily derived in a miscalibration of the probabilistic estimates, that is a future reliability that requires the integrations of the novel matrices such as the confidence entropy and the MTP-CI within such an auditing framework. Now coming to the code, coding of the random def bias update peer likelihood and difference. This program uses a Bayesian theorem for the making a reliable decision on uncertain sensor data. So the Bayesian update which update the bias rule, and the returns a new probabilities for each state, that is a clear or blocked. Now coming to the posterior, that is total is equal to 0.0, that is adding of the missing foreign given in a likelihood state with an evidence at the 0.0, the posterior state and the prior state. So total plus posterior is equals to state. Simulating the sensor data. So if a true sensor is clear, the sensor says the sensor 90% of the time. If the two sensor is blocked, the 80% of the time. Now making of the decisions, gets a single sensor's reading evidence, updates a bias rule and decides if the clear probability or stops otherwise. Now coming to the sensor fusion, the sensor fusion simulates a multiple sensors. Each sensor gives an evidence. The Bayesian update is applied for each sensor evidence. So the majority vote for decision proceed or stop by improving the reliability. Now coming to the reliability test trials, there runs a reliability multiple trials on a test performances with the comparing of the single sensors versus the fusion sensors. It tracks how often each makes the correct decisions, makes us to proceed or stop the cases, and calculates the returns accuracies for both. Now coming to the main sections, that is a one single sensors run with the posterior probabilities and with the one fusion running showing a sensors with the evidence odds and the final decisions. Now coming to the output, this is a running of a single sensors, that is a true state that is equals to clear and the sensor evidence is blocked. So the posterior probabilities and the in the clear state and the blocked state is respectively, and the decision is to stop the vehicle. Now for example, when we are running a sensor, both the sensors, that is a single sensor and the fusion sensor, so the evidence is sensor clear and the odds, that is a clear is the 3 and the blocked is 0, that is none of the vehicles are blocked. So the final decision is to proceed the vehicle with the without any block of the roads. So thank you. This is our small assignment that is given by our Shilpa ma'am. Thank you one and all.